Myself, Dr. PALANIAPPAN, Professor of Physics in the Department of Physics, ANNAMALAI University. And this session, we are discussing about quantum mechanics, a major core paper in the MSc curriculum. It may be a 2-year or a 5-year paper. Any physics curriculum invariably has this topic, quantum mechanics. Not only in master level, also in the research level, this paper is very important. And we may have the very basic introductions of the paper in our UG classes. Of course, we will refresh our idea now also so as to have a clear understanding. So it is quantum mechanics. First, regarding the mechanics. Mechanics refers to movement of particles, motion of particles or bodies or any size. Whenever a particle or a body is in movement, is in motion, we call it as mechanics. Mechanics is of so many types. It may be classified on various bases. And the basis for classification, we are interested on size and velocity. Based on size, we have some classification. Based on velocity, we have some classifications. First, based on size. Based on size, we can categorize mechanics as classical mechanics and quantum mechanics. Classical mechanics is for macroscopic particles, whereas quantum mechanics is for microscopic particles. The term itself indicates bigger size particle and the tiniest particles. Classical indicates a traditional one. It is a mechanics developed some 200-300 years back. The basis for classical mechanics is Newton's equation, F is equal to ma. It is for macroscopic particles or for bigger size particles. Of course, with the developments in science, the development of microscopy, the size of the particle is going on lower and lower. We are to switch over for a new type of mechanics that is applicable for tiny particles. Classical mechanics is not applicable for tiny particles. So, scientists have developed another type of mechanics called quantum mechanics. It is for microscopic particles, those particles which can be realized only through microscopes, like electron, proton, etc. So, based on size, we have two types of mechanics, classical mechanics and quantum mechanics. The most important is we have to be very familiar with the terms, then only the topic can be followed. So, I am repeating again, classical mechanics is for macroscopic, bigger size particles. Quantum mechanics is for microscopic or small size particles. So, one classification is over. Coming to next classification, the classification is based on velocity of the moving particle. If the particle is in motion, we call mechanics. Motion may be slower or faster. That is decided by the velocity. If the velocity is somewhat low or ordinary or as per our day-to-day experiences, we call that type of motions or that type of mechanics as non-relativistic mechanics. Whereas if the motion is comparable to light velocity, light velocity is 3 lakhs kilometers per second, 3 into 10 power 8 meters per second. In 1 second, light can travel for 3 lakhs kilometers, an unimaginable value. It is the fastest physical parameter in the world. If a particle is moving with such a high velocity, we can categorize that type of mechanics as relativistic mechanics. The electrons revolving in orbits in an atom, they are revolving with the speed of light. In atomic fusion or fission, the subatomic particles are moving with such high velocities. So, they are also needed in the day-to-day experiences. So, based on velocity, we have two groups. one as non-relativistic mechanics, other as relativistic mechanics. Or simply saying, slow moving particles or day-to-day life velocities, they are grouped under non-relativistic mechanics. Whereas a very high velocity comparable to light velocity, we put it under relativistic mechanics. So to summarize this slide, we have two classifications based on size and based on velocity. Based on size, classical; based on size, quantum. Classical is for macroscopic particle, quantum is for microscopic particle. One classification over. Second classification based on velocity, slow moving particles represent non-relativistic mechanics. Fast moving particle represent relativistic mechanics. Now I am going to combine these two bases, these two classifications. That is, there may be cases where slow moving particles may be smaller in size or slow moving particles may be bigger in size. Similarly, fast moving particles may be bigger in size, fast moving particles may be smaller in size. That is, I am combining the two bases, size and velocity. Combining these two bases, we have totally four types of mechanics: non-relativistic classical mechanics, non-relativistic quantum mechanics, relativistic classical mechanics, relativistic quantum mechanics. The first one represent, that is non-relativistic classical mechanics, means slow moving bigger size particles. Whereas the second category, non-relativistic quantum mechanics, means a slow moving microscopic particle, tiny particle. Whereas the third one, relativistic classical mechanics, means fast moving bigger size particle, macroscopic particle. And the last one is relativistic quantum mechanics, means a fast moving microscopic particle. So combining the two bases, we have four types of mechanics. For all these four types of mechanics, we need to represent each mechanics by equations. We need mathematical forms. Then only they can be developed and they can be analyzed. So let us see the relevant equations for all these things. The first thing, non-relativistic classical mechanics, that is for slow moving bigger size particles. The energy equation is E equal to p square by 2m plus v. Equations may be force equations or energy equations. Normally force equations are difficult to solve because they are vectors and they have components. So force equations or vector equations are in general not advisable. We have to go for scalar equations. Energy is a scalar quantity, so we are going for energy equation for all categories. So first category, non-relativistic classical mechanics, the simple equation E equal to, E means total energy, p square by 2m is kinetic energy. The kinetic energy form is half mv square, very popular form. The same thing is slightly manipulated as p square by 2m, kinetic energy form, standard form. Whatever may be the particle, wherever may be it, the same unanimous form is for kinetic energy, it is p square by 2m. And V represent potential energy. The equation simply indicates total energy is kinetic energy plus potential energy. Kinetic energy specifically we have given p square by 2m because the same form is applicable for any situation, whereas potential energy is situation dependent, body dependent, so we are mentioning it in general V. The actual form demands the actual situation, actual reason or the origin of energy. So we are using V. It's the first equation, non-relativistic classical mechanics. This is available in our 6th standard to 7th standard, like that, very basic equation. The second thing is non-relativistic quantum mechanics, that is for slow moving microscopic particles. This equation is popularly known as Schrdingers equation. Schrdingers time dependent equation or time independent equation. Both are same. A slight change to include time factor, that's all. But it is popularly called as Schrodinger's equation. That is the equation for non-relativistic quantum mechanics. Non-relativistic quantum mechanics. That equation is IH cross dou by dou t equal to minus h cross k by 2m plus v. In the following slide, I will show you the exact equation. Whereas for the third category, relativistic classical mechanics, that is for particles of macroscopic in nature moving with very large velocity, light velocity, the equation is E square equal to c square p square plus m square c power 4. E is energy, c is light velocity, p is momentum, and m is mass of the particle. This equation is available in theory of relativity in UG classes, in ordinary theory of relativity or special theory of relativity, Einstein's relativistic equation. All these topics have this equation, E square equal to c square p square plus m square c power 4. This is for relativistic classical mechanics. And the fourth category, relativistic quantum mechanics, that is for a fast moving particle which is microscopic in nature, or simply the movement of an electron. What would be the equation? Is a fourth category. This equation is quite unknown. This is the topic of current interest. This equation we are going to derive in this session, and this is a new topic. Only the first three equations are known to us. From the known equations, this fourth equation, which is quite unknown, is to be developed. This question was put in the form of scientists, and each scientist tried to develop their own methodology, their own equation. So one by one we are going to see how they develop the equation, what is their basis for their thinking, and what are the merits and demerits of the equations, and what would be the final equation. These are the topics of interest in this session. So we are moving to relativistic quantum mechanics. Our main aim is to develop a valid equation for relativistic quantum mechanics. Of course, we are not deriving the equation, we are just seeing how the scientists have developed the equation and how they validate the equation. That is the session now. So as I told, we have four equations. The first equation is non-relativistic classical mechanics. Non-relativistic classical mechanics is E equal to p square by 2m plus v. Let it be equation 1. This is for non-relativistic classical mechanics. Now the second category is non-relativistic quantum mechanics. This I have already told, it is popularly called as Schrodinger's equation. It is IH cross dou psi by dou t equal to minus h cross square by 2m into del square psi plus v psi. Here psi is the wave function that is common for any quantum mechanical equation. It may be removed off. If it is removed, then left hand side is IH cross dou by dou t. Psi is removed. Psi is removed in all the terms. So right hand side becomes minus h cross square by 2m into del square plus v. That is in right hand side after removing psi. So this is non-relativistic quantum mechanical equation, popularly called as Schrodinger's time dependent equation. It is having a time factor t. So Schrodinger's time dependent equation. It is second equation. The third equation is relativistic classical mechanical equation. It is available in theory of relativity. Equation is E square equal to c square p square plus m square c power 4. Let it be equation 3. This is equation 2. And the fourth one is relativistic quantum mechanical equation. this is unknown. How to develop this equation? So these three equations, the first equation is non-relativistic classical mechanical equation, is p square by 2m plus v. This is first equation. This is known. Second equation is known. Third equation is known. From these three equations, we have to develop the fourth equation. How to develop and how to validate? These are the issues arises among the scientists in the forum. So the question was given to every scientist, and one by one they try to resolve. There are so many methods, so many theories, so many equations. Our syllabus is having only three equations. How Schrodinger developed the fourth equation is the first question in your unit. Then how Klein-Gordon, KG, have developed the same equation. That is the second topic in the unit. And finally, how Dirac has developed the equation. Only three scientists. The three equations are in the syllabus. We are going to see one by one. First one is Schrodinger again. Here the equation 2 is Schrodinger equation. It is simply Schrodinger equation. But the fourth one is aptly called as Schrodinger's relativistic quantum mechanical equation. If I say Schrodinger's equation, it indicates only equation 2. But if I say Schrodinger's relativistic quantum mechanical equation, then it is for fourth topic. Schrodinger is the first man to develop an unknown quantity, an unknown equation. It is a success of his theory. It is a success of his achievement. Say, a quite unknown thing developed from the unknown situation is a very grand success. That is for Schrodinger. Once he developed, that equation was modified by his successors KG and Dirac. Of course, Schrodinger's equation is having some defect. He is the first man to develop the equation. So first we shall see how Schrodinger developed the equation. Then second, what is the merit and demerit of his equation. Then how the demerits have been rectified by the successor Klein-Gordon, and what are the merits and demerits of Klein-Gordon, then followed by Dirac's concept. So it is the thing what we are going to do in this session. So just I am repeating again, from the three equations given above, Schrodinger has to develop the fourth equation, right? So Schrodinger has put forward two steps only. So in step 1, he put two steps. Step 1, and step 2. In step 1, he just suggested to develop, he suggested to compare the non-relativistic classical mechanics equation 1 and the non-relativistic quantum mechanics equation 2. By comparing these two equations, he is able to relate the classical parameter and the quantum parameter. Or in this equation, E is a classical parameter. Equation 1, E energy classical parameter is E, whereas P is momentum, is again a classical parameter. Here M, mass M, is a universal constant, and V is the potential energy. Comparing these two equations, for classical parameter E, in quantum mechanical equation it is IH cross dou by dou t. Equation 1 left hand side is E, equation 2 left hand side is IH cross dou by dou t. Psi is removed, so E is equivalent to IH cross dou by dou t. Or in other words, E is the classical parameter to be replaced by IH cross dou by dou t in quantum mechanics. So he is able to develop the equivalence of classical and quantum by comparing equation 1 and 2. Similarly, comparing the first term of the right hand side, p square by 2m is equivalent to minus h cross square by 2m to del square. Denominator 2m can be eliminated. So p square is equivalent to minus h cross square del square. Is another equivalence developed by Schrodinger. These are the two classical quantum exchange parameters. once getting classical quantum equivalence, he implement these changes in the third equation, relativistic classical mechanics, that will give us relativistic quantum mechanical equation. Let us see all the steps now. So this is the idea of Schrodinger. So Schrodinger's idea. Step 1, compare equation 1 and 2 so that classical to quantum parameters can be obtained. It is the first thing. If a classical parameter is imposed, then what would be the corresponding quantum parameters? That can be obtained by this step 1, comparing equations 1 and 2. Equation 1 is 1 implies E equal to P square by 2m plus V. Equation 2 implies IH cross dou by dou t equal to minus H cross square by 2m into del square plus V. So compare. E is equivalent to IH cross dou by dou t. Is the very first thing. Let it be equation 4. And the V can be cancelled, and P square by 2m is equal to minus H cross square by 2m H cross square by 2m into del square. 2m may be removed. So P square equal to minus H cross square by del square. Taking square root, P equal to square root of minus and square root of H cross square and square root of del square. Square root of minus is I, H cross square is H, and del square is del. IH cross del. Or in reverse way, if you square, or P square equal to I square is minus 1, H cross square del square. Also, if P equal to minus IH cross del, that also give you P square equal to minus IH cross square del square. So we have two values for P. P is equal to minus IH cross del as well as P equal to IH cross del. Here is one P value, here is another P value. For both P values, if you square, that will give you P square as minus H cross square del square. So the first confusion is whether to proceed with this value or this value, whether P equal to IH cross del or P equal to minus IH cross del. Squaring both the equations give the same value, and we are going to take P equal to minus IH cross del. This value we are going to take because Schrodinger has taken this value only. He suggested no reason to take this value. Why he avoided this value, why he preferred this value, he himself give no reason. So we are seeing how the theory was developed. So as per Schrodinger's development, he has taken P equal to minus IH cross del. So this is equation 5 we have taken now. So we are left with the two equations. By step 1, we have obtained two equations, the equivalence for energy and the equivalence for momentum, or the classical to quantum exchange can be done by step 1. For energy, E is to be replaced by IH cross del and P is to be replaced by IH cross del. E equal to IH cross dou by dou t and P equal to minus IH cross del. These are the classical quantum equivalences obtained from step 1. So one part is over. We are going for step 2. In step 2, Schrodinger implemented or substituted classical quantum equivalence in equation 3, that is relativistic classical mechanical equation. Equation is classical. The classical parameters have been replaced by quantum parameters. The equation will become quantum equation, that is a relativistic quantum equation. This is the idea of Schrödinger. His idea is only in 2 steps. Step 1, he obtained classical quantum equivalences. In step 2, he implemented the equivalence in relativistic classical mechanical equation, so that the equation will become relativistic quantum mechanical equation. Let us see step 2. So, equation 3 implies, that is the relativistic classical mechanics. It implies E square equal to C square P square plus M square C power 4. We have to substitute classical quantum equivalences here. To substitute what we are doing is E equal to, first step, E equal to root of, taking square root, C square P square plus M square C power 4. Substitute E equal to IH cross dou by dou T and P equal to minus IH cross del. So, E equal to, whenever we are taking square root, there will be a plus or minus sign, that we have to include. So, plus or minus C square for P IH minus IH cross del square plus M square C power 4. Making square, we have E equal to plus or minus root of, minus square is plus, I square is minus 1, C square H cross square del square plus M square C power 4. This is the equation. For any quantum mechanical equation, there should be a wave function. Sorry, I have to substitute E equivalence. So, E is to be replaced by IH cross dou by dou T equal to plus or minus root of minus C square H cross square del square plus M square C power 4. This is the equation. For any quantum mechanical equation, there should be a wave function psi. So, multiply both sides by wave function psi. We have IH cross dou psi by dou T equal to plus or minus root of the same thing as in previous equation, minus C square H cross square del square plus M square C power 4 into psi. So, this is the equation. This is Schrodinger's relativistic quantum mechanical equation. Not simply Schrodinger equation, it should be specifically pronounced as Schrodinger's relativistic quantum mechanical equation. If you say simply Schrodinger's equation, then it is in the previous slide. IH cross dou by dou T equal to minus H cross square by 2m into del square plus V. Schrodinger's time dependent or time independent equation. That is normally called a Schrodinger equation. This equation should be pronounced as Schrodinger's relativistic quantum mechanical equation. This is the very first equation developed for relativistic quantum mechanics. Here the left hand side is energy E, whereas the right hand side is having some factors. So, this equation was suggested by Schrodinger for relativistic quantum mechanics. So, a quite unknown thing is now become put forward to some extent, a crude form, a known thing. Schrodinger has developed a unknown thing, but the equation is having its own limitations or demerits. So, what is the merit? It is the very first equation developed in a quite new branch. It is a very major merit of the equation. Defects, the first defect, the energy is positive or negative. It is not accepted in quantum mechanics. As per quantum mechanics, energy can always be positive and it cannot be negative. But as per Schrodinger's concept, energy may be negative. That idea was given by the above equation, and Schrödinger is unable to give the reason for the existence of negative energy. It is the very first inadequacy or the defect of Schrödinger's equation. The second defect, square root of del square. See, del square is an operator. You know operator, what is an operator? Operator is a mathematical manipulation like multiplication, division, addition, like that. Square root of a multiplication, no meaning at all. Square root of addition, square root of del square operator has no meaning. It cannot be interpreted. It cannot be physically, it carries no meaning at all. Schrödinger is unable to answer these two defects. That is the defect of Schrödinger's equation. These two defects are removed by Klein-Gordon in their concept. That is the next topic we are going to see. So with this we are finishing one topic, Schrödinger's relativistic quantum mechanical equation.